So let me welcome you all back for the second talk of this morning. We'll have Samarpita Ray from IISER Pune. She'll speak about lattices, spectral spaces, and closure operations on idempotent semirings. Please go ahead, Samarpita.
1 second, let me.
So before you start, so just because this is a 15-minute talk, maybe we can keep all the questions till the end. If you have questions, please type it in the chat and we will ask them at the end of the talk.
Okay. So,
yeah, go ahead.
Yeah, so I'm going to, this is so first of all, thank you for giving me the opportunity to give a talk here. And this is a recently finished work with Jane June and Jeffrey Tolliver. And before I get to the details, I would like to give a bit of motivation for this work. Now, why idempotent semirings are important objects of study. So this is basically happened with the introduction of scheme theory to tropical geometry in 2016. It was Jeffrey and Noah Giansiracusa who introduced scheme theory to tropical geometry. So tropical geometry is rather a newly developing tool in algebraic geometry, which helps converting questions of algebraic geometry to combinatorial problems by replacing a variety by a polyhedral complex, which is called the tropical variety. So this is where Jeffrey and Noah, they introduced idempotent semirings to give an algebraic foundation for the tropical schemes. Like in algebraic geometry, we have commutative rings as an algebraic foundation for the schemes. In tropical geometry, the notions that are there for tropical schemes has an algebraic foundation by idempotent semirings. And apart from this, semirings have been very useful in rather in the absolute geometry approach of Alan Kohns and Katerina Consoni, which has been like 20 years in the literature now. So having said that, this work is basically our try to add a little to this momentum, ongoing momentum, in which we work with we try to bring certain commutative algebra tools to idempotent semirings, like spectral spaces, connection of spectral spaces, explicit connections with spectral spaces. I'm going to define it with idempotent semirings and closure operations, valuations, etc. on semirings. So okay, let me go to the slides. By a semiring, I mean it's a non-empty set. Basically, it's an algebraic structure just like ring, except that you do not have additive inverses. And if the semiring is having all multiplicative, non-zero elements of multiplicative inverses, then it's a group, and we call it a semifield. The kind of semirings that we are interested in this talk are additively idempotent semirings, which means something that satisfies relation of the form this. Typical examples to keep in mind would be a Boolean semifield and the tropical semifield. This is essentially called tropical semifield because the tropical geometry is based on this semifield. And as you can see from this particular definition that it is an idempotent semiring. So these are the typical example for idempotent semirings to keep in mind. And ideals on semirings can be defined the way you define ideals in rings. And basically you don't have additive inverses, that's the only difference. And ideals by we will mean additive submonoid. So it just means it's closed under addition and you have AI contained in I. By saturated ideal of an idempotent semiring, we mean that if you have two elements X and Y from the semiring such that the addition of those two is belonging to I and X is in I, that also implies that Y is in I. And one can define prime and maximal ideals in the obvious way. That's being said, let's move to spectral spaces. So what are spectral spaces? Spectral spaces are topological spaces introduced by Hochschild in 1969. These are compact topological spaces, which are also T0 and satisfies those two following conditions. So the conditions tells you that the compact opens of these spaces forms a basis, and the finite intersection of compact open is again compact open. And the space is also sober. That means any non-empty reducible closed subspace will have a unique generic point. So if you're familiar with affine schemes or like the Zariski topology on the prime spectrum of a ring, you'd have already noticed that this is what a spec of any ring like endowed with this Zariski topology will satisfy. But Hochschild proved that the converse is also true. That is, a space is spectral if and only if there exists a commutative ring such that the spectrum of it is homeomorphic to X. And this construction is also functorial. Examples are plenty. Space of all ideals, space of all modules over a ring, valuations on a ring, finite type closure operations on a ring. These are all examples of spectral spaces. In fact, if you take any set and you take the power set of it, it is also a spectral space. By spectral map between spectral spaces, we mean a continuous topological map, which pull backs compact open to compact open. In 1982, Johnston proved a very nice correspondence, a nice way of understanding spectral spaces. He proved that the category of spectral spaces with the spectral maps as morphisms is equivalent to the opposite category of bounded distributive lattices. Now, this is a key result that we use to develop the understanding between idempotent semirings and spectral spaces. So we start with very simple question, like let's forget about idempotent semirings. Let's just talk about first semirings. So we know, so we ask this first question, that is it true that the spectrum of a semiring is a spectral space? And the answer is yes, and the arguments are pretty much same as that of rings. So we ask the converse, like is it true that given a spectral space, we will have a semiring such that whose spectrum is homeomorphic to X? And that is also kind of tautological because all rings are semirings. So the question that we actually ask, or we actually want to understand, is about idempotent semirings. So given a spectral space, the question is, can we find an idempotent semiring which such that the prime spectrum of that idempotent semiring is homeomorphic to X? Now note that an idempotent semiring can never be a non-zero ring. That's a typo. It's a non-zero ring. It cannot be a non-zero ring. So, and we answer this question in affirmative, but we have to restrict ourselves to a subclass of the prime spectrum of the idempotent semiring, which we call saturated. This means that the prime ideals, which are also saturated ideals, that is the saturated primes. And we prove this, that X is a spectral space, then there exists as idempotent semiring, and this existence is a canonical way of associating. And for this, we appeal to the Johnston's understanding of the connection of bounded distributive lattices with spectral spaces. And Hochster's way techniques didn't work for this. So Johnston's result is what we used. And now, if you have that, it's natural to ask the converse, like, is it true that when you have if you're given the saturated prime spectrum of any idempotent semiring, is that a spectral space? And that is also true. As I mentioned, and let me explain why. So as I mentioned before, that given any set, the power set of any set is a spectral space. Endowed with the Hull kernel topology, which is given by the open subdiscs are given by these subsets of this form. Now, yes, you must be wondering, is this the kind of similar to Zariski? And yes, if you are in the right setup of rings, then yes, this goes down to Zariski topology. But induced with this Hull kernel topology, you can prove that the collection of all ideals, collection of all proper ideals, prime ideals, saturated ideals, these are all spectral spaces. And, and in particular, what we wanted that to understand the saturated primes of idempotent semiring, and this also, through this, we also show that this is any saturated prime spectrum is going to be a spectral space. So what we have essentially is this, that a space is spectral if and only if it is homeomorphic to the saturated prime spectrum of an idempotent semiring. But what we have is more. We have a categorical equivalence, which wasn't there for rings, because you already know that the category of commutative rings, it is equivalent to the opposite category of affine schemes. And so what we prove in this, let me first give the result and then I will get back. So this is the main result, that we prove that the category of this radical idealic semirings, this is a subcategory of the category of idempotent semirings, subclass, okay? And that is equivalent to the opposite category of spectral spaces. In other words, spectral spaces in the level of like morphisms and spaces itself, like the entire category is captured by semirings and than rings, which didn't hold for rings. So that is basically also the essence of using this more general algebraic objects like monoids and semirings. This is what Consony and Alan Kahn's idea was related to this. I mean, sometimes when the thing is, sometimes when you look beyond the category of commutative rings, like more general algebraic structures like rings and like monoids and semirings, sometimes it helps you to give more information about certain spaces. And this is kind of an example, small example, where you can see this to be true. So yeah, so now I will get to congruences. So let me talk about congruences. Yeah, so congruences, basically these are equivalence relation on a semiring, and which respects addition and multiplication. In case your semiring is a ring, there is no difference between congruence and ideals. However, in case of semirings, congruences and ideals are not the same. There is no one-to-one correspondence, because I mean, the ideal associated to a congruence is given by the kernel of the congruence, which is this. And if you look at it carefully, you will see that it is clear that you can have two different congruences, which gives rise to the same kernel, which has the same kernel, that is the same associated ideal. So there is no one-to-one correspondence, and that is why there is two different theory when it comes to the development of tropical schemes. One is via use of ideals, like prime ideals, and the other one is the use of prime congruences. Now, what are prime congruences? Prime congruences were defined by Daniel Zhu and Kalina Mencheva in 2018, and the way they defined is they used a notion of twisted product between between elements of the congruence given by this, and they defined congruence to be prime if this condition is satisfied. So this is the congruence prime spectrum associated to a idempotent semiring, and we find something quite nice when working with the valuations. So valuations, by evaluation of an idempotent semiring, I mean a homomorphism, simply a homomorphism from A to gamma max, which is this semifield. And what we have is this result that, first of all, for any idempotent semiring, the valuation spectrum, which means the equivalence class of valuations on the semiring, that is a spectral space. But what we obtain is a very nice bijection, a natural bijection between the valuation spectrum of A and the prime congruences on A. Now, this is interesting because, as I said, in case of rings, congruences and ideals are no different. So has it been true in case of rings, then what we are saying is, in case of rings, we would have got that the valuation spectrum of a ring is in bijection with the spectrum of a ring, which isn't true. And for that, you can take the example of the ring to be the rational field. Okay, so next we move on to closure operations. Now, closure operations on which we introduce in this work is basically, the definition is pretty much similar to the closure operations we define in case of rings, ideals over a ring, extension, order preservation, and idempotence. And you can talk about finite type closure operations just as if you were in this classical setup. And you can prove, and what we proved that is that the the finite type closure operations, they form a spectral space. And I mean, whenever I'm talking about certain results in terms of ideals, I've also done that for congruences to keep that simultaneously going. Because what are better options, ideals or congruences for tropical schemes is still not settled. And as part of this work, we introduce integral closure operation and Frobenius closure operation. So by integral closure operation, this is what we define. So basically, first you take an ideal, you take the I int to be the collection of all elements which satisfies a relation of the form this, each ai belonging to I power I, and then you consider the intersection of all saturated ideals containing I int. That is what we define to be the integral closure of I, and we define this to be the integral closure operation considering the classical integral closure similarity with classical integral closure. And yeah, so, and we also develop connections with valuations and integral closures in our work. I have skipped that here. And next, I just have one more thing to say is the Frobenius closure operation. So for an idempotent cancellative semiring, by cancellative, it's similar to the idea of integral rings, no zero divisors kind of situation. And yeah, and in that case, you can solve, it's kind of a slightly non-trivial proof, but you can show that for any natural number n, this map A going to A power n actually is an endomorphism of an idempotent cancellative semiring. This is not in general true. You have to take a prime, and therefore Frobenius closure is always defined for a prime. But in this setup, we can define Frobenius closure for any n. And apart from this, we also introduce other closure operation on congruence relationships, like the congruence relations that I've just talked about. And that pretty much sums up the work and that we have done. And yeah, so here is some of the references for this work. And yeah.
Thank you, Samarpita.
And thank you for giving me the opportunity.
So there is one question, maybe now two questions. Can you see the chat? Should I read this to you?
Let me see if I can see the chat. Where is the chat? Once.
It's, I don't know where which you are using, but let me just read it. Why only idempotent semirings?
Yeah, so idempotent semirings, as I said, these are the algebraic foundation for tropical schemes. And this is what I was talking about at the beginning of the talk, that like commutative rings forms the algebraic foundation for classical algebraic geometry. What has been introduced recently roughly from 2016 is these notions of idempotent semirings, on which basically the notion of tropical schemes are developed. So that is why specifically idempotent semirings is our interest.
Okay. And then how are congruences and ideals different for semirings?
So as I go back, so one can give, of course, specific examples, but let me just go back to the slide so that I can have. So let's see here the correspondence between ideals and congruences. So the thing is, when you work with rings, you have the additive inverses, that is the subtraction. And that is exactly what helps you to prove that this correspondence that you have is an isomorphism, like there's a bijection. But if you do not have additive inverses, then that doesn't happen. For example, you can see here, you can choose congruences easily, which have, so this is called the kernel of a congruence, and it's an ideal. So this is the associated ideal, the ideal that you associate to a congruence. So if you see it carefully, it is just possible that you will have two congruences such that so what does it mean? It means the ideal associated to congruence is the collection of all the elements of the semiring which are equivalent to 0. So it is absolutely possible to have two different congruences in which the elements which are equivalent to 0 are same. So you have two different congruences but the same kernel. You don't have a bijection.
Okay. Well, can you give some examples of idempotent semirings?
Yeah, that was the first slide. It's always better to look at the slide rather than saying it. So these are the typical examples to keep in mind, but you can of course cook up, you can construct some idempotent semirings as well, just by quotienting. But these are some typical examples to keep in mind.
Okay, so maybe one more. What is the need for these particular closure operations?
Particular closure operations in the sense I talked about only integral and Frobenius closure operation. So as far as I understand, integral closure, so let me go to the slide first. So integral closure operation in general has some very important geometric application. For example, like when you take integral closure of so closure operations is basically a way of extending some ideals. So, and in doing that, specifically for integral operations, you can remove certain singularities from the ideal, or rather the scheme that you're working with. So that's how this operation. This is what I understand, like the geometrical relevance.
Okay, so thank you, Samarpita. Let's thank her for a very nice talk.
Thank you.